the recording then. Great. Okay, so welcome to this lecture where I will introduce a couple of concepts within deep learning and deep neural networks specifically that hopefully will help you understand homework C. And I will be broader than only homework C, of course, but at least the key concepts that you need for that task will be covered. So I will, let's see, I will share my screen. Good. So now you see my presentation, I guess. I'll assume so. Great. So as I said, this will introduce this or some key concepts within the field of neural networks and deep neural networks. So I will start. From the beginning. So what is a neural network? Since you've probably already had the introductory course in neural networks, I guess you'll already know this, but anyway, a neural network consists of many neurons that are interconnected. And each such neuron takes a series of input. So in this case, you have the inputs here, x1, x2, x3. They're passed through a linear transformation. And secondly, they're passed through an activation function to produce an output. And in a network, of course, you don't have only one such neuron, but you have many. And in principle, you can divide networks into classes depending on their depth. So for instance, here you see a shallow network consisting of only a single layer of such neurons, while you can imagine stacking such layers on top of each other to create a deep neural network. So there is a theorem saying that in principle, one layer is enough to map arbitrary input to an output through an arbitrary function, basically. So in principle, then, this theorem states that you will never need anything more than a single layer of neurons. But anyway, there is this huge hype regarding making the networks deep. So then one can ask oneself, why do you want to make the networks deep? So we can think of this in several different ways. And I was actually thinking that just to kick this off, considering that, it's early in the morning, and I think listening to me speak for 2 hours is going to be a bit boring. So I was thinking that we can actually kick this off by letting you discuss this concept. So the question is, why do we want to use deep networks? Why do we want to stack many such layers of neurons instead of using just a single layer of neurons? What is the benefit, and where is the limitation? Can we make these networks arbitrarily deep, or is there some kind of limitation to it? So I'll sharing here, and I will see. So why do I not see the option to make breakout rooms? Could be that I have to be the host, exactly. That is fitting. Okay, so instead of making breakout rooms, then
Daniel, I can make a breakout room for you. Sorry.
Yeah, okay, that would be good. Can you make it so that I can actually make breakout rooms?
I don't know how to do that, but just tell me what you want and I do it.
Yeah, but okay. So split them into groups of 5.
Okay.
But I will. Okay,
I can try to make you host. I can make you host actually. Then you have full power. Okay. Now you are host. You should be able to.
Now I can make breakout rooms. Yes. Okay. Perfect. Okay, thanks. Then that's fine. Great. So now I've invited you to breakout rooms, and we'll reconvene in 5 minutes. I can share my screen again and see the questions. So what I will do is, to make this kind of useful, I will share my whiteboard, and yes, you should be able to annotate here. So please, if you can just anonymously write some keywords of what you have discussed on the whiteboard, and then we can, that would be great. I will also resume the recording. I think you can also write with text, although at least I can do that. I think you should also be able to do that. Yeah, so we have the vanishing gradient problem. So that refers to the fact that if you have a very deep network, when you optimize the weights, you have to propagate the error through many layers, and then you have a problem that the first layers might not contribute as much to the training due to this vanishing gradient problem. That's true. That's actually a very good point. Specialized layers. So different layers can specialize on different tasks, I guess. Is that what you mean? That's also a good point. We also have a comment in the chat that the number of required parameters scale better on depth than in width, and that is exactly exactly true. That if you want to create a single layer network that maps your input to an output, you will need extremely many neurons, and this is not a very efficient way to construct a network architecture. Yes, deeper networks can learn more complex features and learn different levels of abstractions, and that is a point that is very often brought up. these. So there's a question: do you require fewer neurons in total if you have multiple layers? I'm not sure. I don't. Yeah, it's that is a very good question, and I don't think I have a definite answer to that. I think the point is that having multiple layers is usually easier to train, and can, as was pointed out also, you can learn different layers of abstraction, so you can learn features with different hierarchies using multiple layers. There might be a difference in how they generalize also. Yes, deeper networks might generalize better. Yeah, there are many good points here, I think. So clearly you have some kind of intuition about how these deep networks work, which is great. So with regards to the vanishing gradient problem, I think all these points were perfectly valid. And with regards to the vanishing gradient problem that you have when you have a very deep network, I just wanted to kind of show how it works, although I think most of you might already know this. So the way that you train a neural network is that you have a ground truth, a set of data where you know the ground truth, and then you pass this data through the network, so through the neuron here, and in this case it's a single neuron network just for visualization. This produces an output, and then you compare the predicted value from the network with what you expect from the ground truth. And this comparison is quantified through what's called a loss function. And in the next step, what you do is that you propagate the error that you made through the network to calculate how you update the weights for the next iteration. So that is how it works in general. But it's very important to remember that while the point of networks is generally to perform well on data that is not seen before, the only thing that you actually do is to optimize the performance of the network on the data in the training set. So just because you have a network that performs well on your training set, does absolutely not mean that you have a network that also generalizes to other data that it hasn't seen. So what one typically does is that one splits the data. So you have one part that is the validation data and one part that is the training data. So the network is then trained using only the training part of the data, and it's validated on the validation data, of course. So the weights are never optimized or never updated based on the output of the network when it sees the validation data, and that is a very crucial point. And what you typically see then is that in the initial phase of the learning, the training and validation loss follows each other, while after a while, the neural network starts to perform significantly better on the training data than on the validation data. And what that means is that the neural network starts to learn very specific features that is present in the training data, but not present in the validation data. So that's the point where it starts to specialize on the training data and start to lose the general features of the data that are kind of important for predicting well on unseen data. So you want to hit the sweet spot before the validation data starts to become worse. So that's the typical way to train a neural network. But this leads to a fundamental problem, namely that typically what we do is that we benchmark how machine learning algorithms perform against how a human would do the same task. So that's how you do in image classification, for instance, or in recognizing handwritten digits, as in the previous slide. You compare the machine learning accuracy to that of a human. And of course, normally the machine learning algorithm is some percentage of the human capacity. So let's say that the state-of-the-art image classification manages to do 98% accuracy on a certain given data set. That means that in 2% of the cases, the human and the machine learning algorithm did not agree on the classification. So of course, the benchmarking against human capacity is natural, since humans are, after all, generating the training data. So humans are looking at these images and classifying them in terms of them being cats or dogs or cars. So then that is the only way to benchmark it. But how do we actually know that the humans in these 2% of cases that the machine learning algorithm and human classification differed? How do we know that the humans actually performed the classification correct? So more broadly, how can we extend the capacity of neural networks beyond what humans can do? I mean, if we want this to be really useful, one can argue, you don't want it to classify images of cats and dogs almost as good as a human can do. You want it to do a task better than a human can do. But it seems that this is kind of not possible if you use humans to also generate the training data, so that you use humans to determine whether the neural network is performing good or bad. So that leads us to a second breakout session where I want you to discuss this. So is it actually possible to use machine learning algorithms to do something that humans cannot do? Or is it just a way to automatize something that humans can do? And if there is a way to enhance the performance beyond what humans can do, how can we then validate the results of the network? How do we know that the network is performing correctly if they do something better than humans can do? Yeah, that's a question. How to data augment? Yeah, that will give you more data, but I don't see how it will help in this case. I think it's useful to have this discussion. I will generate breakout rooms again. Whiteboard again, so you can write your thoughts there. So we have some suggestions. So one point, if I understand it correctly, is that the artificial intelligence will only see the data that it is kind of given, while humans have access to all kinds of data to generalize to fine-tune our own neural network, which means that kind of we will always have a broader scope, perhaps, than a single neural network, and that is true, of course. We have the suggestion of unsupervised learning. That's true. So if you, there are ways to not split data into, or well, not provide a ground truth to the networks, but that the networks actually learn themselves what they should optimize. That is one way to enhance it. Q-learning might be another.
I just wanted to clarify, like what I meant by this, that the AI can have more data is one person in our group had a really great example that if you look at a cancer tumor, the AI would only see the image of the cancer tumor, but and a human could know, like 1 year down the line, did the person suffer from this? Like, did it turn into an illness?
Yes.
So you can have metadata, which is like more than what you're presenting the AI.
Yes, that's a very good point. So that is always going to be a limitation of networks. That's a good point. We also have some genetic algorithms as proposed. In certain tasks that can be used to improve performance in, yeah, sure. But this is actually a very, I think this is a very interesting topic, because most applications, not all, but many applications of neural networks focus on trying to get the network to perform as good as a human. But that is not necessarily what you want it to do. You might want to go beyond that, and then you need to be kind of innovative to manage that, I think. Yeah, and a different point is that computers, of course, they can do the processing a lot faster. They can do it automatized. So in that sense, they are of course better equipped to handle big data. I mean, if we want to classify 100,000 images, that is going to take a long time for us, while for a computer it's going to go a lot faster. So I mean, in that sense, computers are already outperforming humans. But in terms of accuracy in classification, that is not necessarily the case. Yeah, that's an interesting idea. Perhaps annotating simple data and transforming it into a more difficult problem. That's an interesting idea. Actually, the question is, I guess, how to transform it in such a way that it actually represents some kind of useful data. But yeah, that's a very interesting idea. Actually. Okay, so let's go on. But as I said, this is something that I spend some time thinking about when I do my research, which is in deep learning based or deep learning enhanced microscopy. There I often employ deep learning solutions to classify microscopy images, but the question is, when is this actually meaningful? That is, when is it better to use a deep learning approach than to actually classify it yourself, if the deep learning approach anyway doesn't actually do it better than you can? And secondly, if the deep learning approach appears to do some kind of classification task better than what you as a human can do, how do you know that this is actually correct? That is an extremely tricky question that one has to be able to answer somehow. Great. So we have a couple of minutes left on this part of the lecture, the first part. So I will go on and start to discuss some of the extensions of this very simple model that we have looked at so far for neural networks, which I think you're anyway kind of familiar with. Let's see. So what we've looked at so far are so-called dense neural networks, since each node in every layer is connected to each node in the next layer, right? And of course, this scales very poorly with the size of the input. So for instance, if you want to classify an image, then each pixel in this image would represent one input. And then you want to connect this to a second layer. Each pixel has to be connected to each node in the next layer. And then you realize that this is going to be a very big network if you want to do even a very simple task like classifying images, small images like this. And the second point is that if you want to analyze time sequences, the network inherently doesn't have any sense of time. So it doesn't know which input is the first and which input is the last, and how they are connected temporally. So you might be tasked with a more difficult problem to assess whether this parrot is happy or sad, for instance, based on a video sequence like this, and the dense neural network wouldn't know how to begin performing such a task. So somehow we have to generalize this concept. So the problem with dimensionality is solved more or less using convolutional neural networks. So in this type of networks, instead of connecting each pixel in an image to each node in the subsequent layer, what you instead define are a set of convolutional filters that are applied to the input data. And it is the values that go into these different convolutional filters that are what the network is trying to learn. So each filter acts on the input data to generate a feature map. So it kind of highlights certain features in the image that might be interesting. And the weights of the convolutions or the values in the convolutional filter determines basically what features the network will focus on. So in this case, the task is to take an input image like this, which is a macroscopic image of a small particle. It's cropped around this particle then, and determine its position. So I mean, as a human, we can see that the position is somewhere here. That's kind of easy. And to solve this problem using a convolutional neural network, you initialize the network in some state. So you have a set of such convolutional filters with random weights in the beginning that extracts then random feature maps. And in the next step, what you do is that you downsample the image. Downsampling helps the network to see features at different spatial scales. So if you think about if you have this kind of 3x3 filters, in order to classify or characterize a certain pixel, it can only see the neighboring pixels, right? But if you then downsample the image, each pixel can suddenly see data coming from 2 pixels from each side. And if you downsample it again, you can see 4 pixels away. So in that way, you can learn different spatial features with different spatial extent by downsampling data in this way. And then in the end, when you've downsampled it a couple of times, you connect this to a dense neural network to produce some kind of output. In this case, the position of the particles, so the x and y position. So let's say that we do this. In the beginning, of course, we will have some kind of poor estimate of this because the weights of the convolutional filters are randomized, and we propagate the error backwards as we discussed before, and you will get a better and better estimate of the position again. So this is how convolutional neural networks work, basically. And typically, they don't look like the very simple schematic that I showed before, but you have stacks of blocks of such convolutional layers, followed by some kind of downsampling to compress the data in the image to allow the convolutions to act over a larger spatial scale. And then you compress the data again by another pooling layer. And then the convolutional features can see even further away. And then you do this a number of times, depending on the size of the input image and the spatial extent of the features that you actually want to look at. And in the end, typically what you have is some kind of dense network in the end, which produces an output if you want to do some kind of classification, or in this case, a regression, determining the position of the problem. And these convolutional neural networks, although they are conceptually very simple, I would say, they are also extremely powerful. So one example of how this has been used is in, let's see if this starts now. Appears to have died. That's not optimal. Just hang on. And what's on this? I think the problem was that I wanted to display a YouTube video probably, and my computer thought that was a bit dangerous. Okay. So here we have then a video with cars and people. Let's see if it starts now. Yes, cars and people. Oops, it's a bit glitchy, but okay, anyway. Cars and people being recognized by an algorithm called YOLO, which stands for You Only Look Once, which is based on a convolutional neural network. So each pixel in each frame in this video is kind of classified as being either a car or a person or background, so neither a car nor a person. And based on this information, it manages to pinpoint the locations of basically all cars and all people in each frame. Yeah, it's really glitchy. So this YOLO algorithm is kind of, yeah, it's the state of the art for recognizing and tracking objects in videos. Another example of where convolutional neural networks comes in that is also relevant for homework C is in autoencoders. So the autoencoder, the task of an autoencoder is to basically recreate the input image, which seems as a kind of meaningless task, but it's actually not, which I will explain. So the way it works is that you have an input image. The network downsamples the image first in this step. Here you have this downsampling path, so you compress the image into being smaller and smaller, right? And at the same time, you increase the number of convolutional filters that act on the image, which means that you extract many different features at several different scales. So that is the encoding path of the autoencoder. And then you have the decoding path, which basically reverts the action of the encoder to create the original input. And the point is, if this works, what you have here is actually a compressed version of your original image. So this is a way for data compression, since the amount of information here is necessarily sufficient to recreate the image. That means that this has to contain all the information that is needed to, all information content in the original image has to be contained within this very small bottleneck of the autoencoder. So it's a way for data compression. And in the context of the homework, the point is that using an autoencoder like this allows you to reduce the dimensionality of the input data. So in homework C, what you will do is that you will, if you choose to do it, that is, predict the next video frame in sequence using an attention mechanism that I will explain at the end of this lecture. And by compressing the data in this way through an autoencoder, you can apply the attention mechanism on a compressed version of the original data, which is a much lower where the data has a lower dimensionality than the original data, and therefore is easier to handle for a neural network. So that is the key idea of autoencoders. But I think, okay, I will actually show one more thing before the break, because that is what I had planned, and we're almost in time. The final thing that I wanted to show, not spend too much time on, is a type of convolutional network called the U-net. And the U-net term relates from the kind of U shape of the network. It's kind of similar to an autoencoder in that it has a downsampling path here. You downsample the image and then you upsample the image again. But here you don't just recreate the original image, but you generate some kind of useful representation of the original image. So in this case, what you have as input are microscopy images of cells. And what you have as output are regions, masked regions, where the cells are located in the original image. So that's called segmentation then in image processing speak. And the way that, so units transform from image to image. And the difference between units and autoencoders is that you're not interested in compressing the data per se. What you want to do is to generate a useful representation. So what you can do is that you can use skip connections, because if you think about what you do when you do a convolutional neural network, for instance, whenever you downsample, obviously you lose information from the spatial. You lose spatial information, right? Because you compress the data in some way. Sometimes this can be retained anyway, but in other cases it cannot be retained. So in order to make sure that the information that you extract in early layers of the encoder, where you have access to fine details, is actually preserved when you generate your output representation, what you do is that you have these skip connections. So you do some kind of convolutional transformations, and then you have a connection directly from this initial layer where you have fine detail to the last layer to kind of ensure that the fine details are kept in the final representation of the data, or to give at least the network the information about the fine details. And this you do at each step of the unit in a way to keep the information that you lose from your downsample. So that's kind of a, yeah, that's just a neat trick that you can do. And that's basically what I wanted to say about units. So let's see, there was one thing in the chat. Okay, but anyway, I think we will have a 15-minute break now, and we convene at, let's say, 9:10 then, and then I will do the second part where I will talk about some more advanced ideas in deep learning. Let's start again. I will resume the recording. So I got a few questions, 2 questions specifically at the end of the first lecture. The first one was how to train a unit. And I will share my screen again. So the way that one does it is basically in the same way that you train any other neural network. So usually what you do is that you, let's say that you want to find where cells are in this image. What you do is that you ask an expert to look at 1,000 of these images and draw contours where he thinks cells are. And from these contours, then you can create these kind of these masks that you see here. And those masks are then used as ground truth for training the network. So that is how it's usually done. So in the end, what you have is the network outputs some kind of image, and then you compare that image to the ground truth image, which is what the expert has decided is the ground truth. And then you do some kind of analysis on a pixel by pixel basis, usually if the network analyzes this pixel correctly up here, and if it analyzes this pixel correctly up down here, for instance, and those are then weighted together to get a final loss score, which is then used to update all the weights in the network. So the second question that I got was why one uses dense layers at the end of a convolutional neural network. And that is a very good question, because that is actually not strictly needed. Of course, you can it depends. It depends a little bit on what you want to determine, perhaps. But you can imagine that for instance, if you want to classify an image, and what you can do is that you can simply downsample the image and then let to a smaller dimensional representation of the image, and then let different regions, different patches of the image produce its own classification, and then you average those classifications in the end without using any dense layers at all. That is certainly possible. In some cases, this is a good idea, and in some other cases, it might not be a good idea. It depends a little bit on the context. But it's absolutely not necessary to use dense layers in the end. Let's see. For some reason, I can't open the chat when I have a screen share. Great. So, as I said, we will have a few more concepts now, slightly more advanced. The first one that I wanted to show you, although it's not maybe explicitly used that much in this course, but I think one should know about it if one has had a course in advanced machine learning, is the concept of adversarial networks. So here's an example where Salvador Dali has been reconstructed, revived from the dead using artificial intelligence. Let's see if I can make it play. No, I cannot. Okay, I don't know. It doesn't want to play, but anyway, I think you have all seen these types of videos where you generate extremely realistic looking images or videos of people that say or do things that are not true. Right? The deep fake thing. So how is this done? So in general, generative adversarial networks consists of two parts. So you have a generator and you have a discriminator. The generator is a neural network which generates fake images, basically. So just to give an example of how this might work, I will go through what we did in a recent project where we, in our group, developed an adversarial network for converting between different microscopy modalities. So the task is to take images from one microscope, which you see here, and convert them to the corresponding images if you would have used a different microscope. So these are bright field microscopy images, and these are fluorescent microscopy images. So two different types of microscopy. Okay, so the generator in this case is based on a UNet. So it downsamples the images, the bright field images, so the input images basically. And then it upsamples it again, and then you have these skip connections. And in the end, it outputs a new image, which is what it thinks then the corresponding image would look like if you would have imaged it using a fluorescence microscope instead. And as you can see, this is not a very good image that the generator can produce by itself. So that's why we also use a discriminator to train these types of networks. So the discriminator is an encoder, so it's a convolutional network that discriminates between real images and fake images. So for instance, if we feed the discriminator with a real image, which is what the corresponding image should look like, a real image, then the network downsamples this image and produces an output corresponding to whether this image is a real or a fake one. And in this case, since we have real images, it will also output real as a prediction. And similarly, if you feed it with fake images produced by the generator, the output will be fake. And the idea is that the opinion of the discriminator, whether the input image that it gets is fake or if it's a real image, is used to train the generator. So that the generator tries to fool the discriminator. The task of the generator is to produce sufficiently realistic images that the discriminator doesn't know if the image that it gets is real or fake. So with time, if we do this kind of training scheme, you will see that the generator becomes better and better at creating these images. But still, they're not very good. So the discriminator can easily say that, okay, this is actually a fake image. But after a while, you actually end up with extremely good-looking images that are very, very realistic. And at this point, you have reached a sweet spot where the discriminator doesn't know what to output. So that is how generative adversarial networks work. And this is, as I said, it's the technology behind this deepfake thing, where you generate extremely realistic images of, well, often famous people and make them say things that they. So I think it's useful because this is actually a very important topic, I think. What are actually the risks behind using generative adversarial networks and deepfake? Are there any ethical considerations that one should have when one creates new deep learning solutions? So I want you to discuss this in a couple of breakout rooms. I will, since I have quite a bit more that I want to say, I will not make it 5 minutes. I will only make it, I'll make it 4 minutes instead. To give us a little bit more time. Okay, so see you in 4 minutes then. To write down a few ideas that you had on the whiteboard. Video evidence, for instance, yes, that's a very good example. If we how do we trust video recordings as evidence in trials, for instance, or in any setting? How can we trust anything that we see? Misinformation is that's a very big risk. I think the image recognition idea there was kind of interesting. Do you think, can you elaborate what you mean? I think another, I mean, in general, I think this is kind of an example of what can happen when we train neural networks to do something better than what a human can do. I mean, in this case, you have it's not exactly it's a variant maybe of unsupervised learning, that the discriminator actually becomes better, I would say, in many cases than a human in classifying whether an image is real or fake. So this kind of brings us back to the topic that we discussed before. Right. Yes, I see what you mean. If you fool self-driving cars, yes. Yeah, that would not be a very good thing. That's true. But that's clearly a risk. You can hack computer systems in cars, and also to, yeah, that's a very good point. But I think this kind of shows also a little bit about the risks of making neural networks outperform humans. That you can think of many ways to make them do bad things that you don't want them to do. And the discriminator in this case is, yeah, I think that's kind of an example of a neural network that outperforms humans in classification tasks. So this is actually one way to generate that. Cheaper Hollywood movies, yes, that's that's also a good point. I mean, they are maybe less salary to movie stars also can be an extension to that. Okay. So we identified some risks associated with this. So in the last portion of this lecture, a bit more than 50 minutes, I will also talk about how to learn data that comes in a sequence. So examples of that include time series and translating sentences, right? That are kind of archetypical examples. So as we said, dense networks, they have no sense of time. All nodes are connected to all other nodes. And there's no way for the network to know whether a certain node is the beginning or the end of a sequence. And this is, of course, important information if you want to analyze time series. So one way is that you can maybe use convolutions. But the problem with convolutions is that, I mean, in some cases, for instance, if you want to analyze sentences, the last word and the first word might be connected. This is so. This is in particular true for translation. It's not as true for analyzing time series, where you can actually imagine that convolving a very local part of the time series might actually provide sufficient information to predict later on. That it might be true for certain time series, but it's not definitely not true for translating sentences. So there's been quite a bit of work done on trying to encode some kind of memory in networks. So the basic building block of memory networks has traditionally been the recurrent neural network. So the idea is that you input the data sequentially. So you start from X1 and you have this network layer that produces some kind of output. And this output is used in the prediction of the subsequent step and so on. So in the end, in theory, when you analyze the final data point in the sequence, whether it's a word or it's a time series of data points, the output of that layer, the recurrent layer here, will have information from all time points in the past. That's the idea. But it's very difficult to learn long-range dependencies, just as for convolutional neural networks, where the output from this node will be a result of the output from the adjacent node, basically, or will depend on the values in the adjacent nodes. The same kind of goes for recurrent neural networks. If you have a long sequence, whatever the network predicted in the beginning will have very little influence on what the network predicts in the end. So it's very difficult to learn long-range dependencies. And the reason is that you have this vanishing or exploding gradient, or well, yeah, it's vanishing gradient problem, that when you propagate the error backwards, the wait for updating based on the output from the first few data points in the sequence will have a very low weight. So it will not really matter much what the network does in the beginning. The important thing will be what it does in the end. It's not really utilizing the full sequence. So that's not very good. So one way to solve this was proposed to be the long short-term memory layer, which is more complicated, as you can see. So the in this little GIF here, what you see is that the input is fed through this this gate here, and the output, it produces two outputs here and here. And you see that the lower output here, which is called the hidden state, is concatenated with the input from the next state, from the next data point, while the cell state, which is the state up here is simply fed through the network. And within it, there are a number of operations. It looks kind of complicated, but I will try to explain how it works. So you have, let's start with the cell state. The cell state is up here, and it is updated as a weighted sum of the previous values of the cell state, together with a transformed version of the current hidden state. So this is kind of the memory term of the network, you can say. The forget state, the forget gate, is this one. It determines how much of the previous cell state should be included in calculating the next cell state. So you see that here you apply a sigmoid function to some kind of transformation of the input, which transforms it into a value between 0 and 1, right? And then you multiply this with the previous cell state. So it means that you can either forget completely the previous cell state, if this is close to 0, or you can remember everything of the previous cell state if this is close to 1. And to this, you then add the result from the input gate, which is another transformation of the input to produce the new cell state, which is then passed on to the next layer. And then apart from this, you have the output gate, which performs another transformation of the input data to produce an output, which is then I was going to say a weighted sum, but it's not a weighted sum, but it's a product of a transformation of the cell state, which is the memory, with the transformation of the current input. So this transformation here means that you will have information about previous, retained information about, or selective information about previous steps, basically. So this is, in essence, how a long short-term memory works. And it's, as you see, it's a bit complicated. And it still only partially solves the problem with vanishing gradients. You still have this problem that if you want to learn very long-range dependencies, you will still have vanishing gradient problem. So the question becomes, of course, can one make this easier in any way? Easier for the network to learn this? And in fact, pretty recently, there's been a lot of development on that area. Okay, so we have a specific question here. Why is the input gate a product of a tangent hyperbolic and a sigmoid function? Let's see if I can answer that. Yeah, that's a good question. I think I will have to get back to you on exactly why that is. Aha, no, it's like this. It's like this. Okay, now I remember how it is. So the hyperbolic tangent part is to regularize the input data, right? You want it to output some values that you don't want it to explode. So you want to keep it between between -1 and 1 somehow. That's the tangent hyperbolic part. And the point with the sigmoid function is that you choose how much of the current data you want to pass on to the cell state. So how relevant is this current data point for updating the memory of the network? So how much of the current state should be passed on to the next LSTM layer in the cell state? So this can be close to 0, and then the current state will not, the cell state will not depend at all on the current state of the LSTM, or it's close to 1, and in that case, the cell state will heavily depend on this particular time point. So, for instance, if the forget gate is 1, then and the input gate is 0, then you can see that the result of the LSTM network at this particular time point will be completely forgotten in the next time point, because you don't add any information at all to the cell state. While in the opposite case, for instance, if you have a forget gate that is 0 and an input gate that is 1, it completely resets the LSTM network so that the cell state suddenly becomes dependent only on the current evaluation of the LSTM data. And of course, intermediate values of the forget gate and the input gate will give some kind of intermediate between those two extremes. That is the reason. Okay, so this is a little bit complicated. So enter then the attention mechanism. This has been a huge hype or a huge development. I don't want to call it a hype because I think it's probably quite useful. And this mechanism is inspired by how the brain works. So for instance, when we look at an image or a sentence, we don't maybe look at the entire image at once. We look at certain parts. So if you look at an image of a person standing next to a tree, you probably first look at the person, maybe first at the face of the person, and then at the person as the person as a whole, and then secondly at the tree. So we attend to an image at different spatial scales to infer some kind of information about an image. And the same goes for sequences, like sentences. We might want to focus, in order to interpret a sentence, we put more focus on certain words than on other words. So the question is then, how do we leverage this in neural networks? And one attempt to do this is through this attention mechanism. So the idea with using an attention mechanism is that it can explicitly select related information in a sequence. So the memory of the memory in a network, in an attention network, is composed of this what's called key value pairs. That's a K and B here. And what it does is that it takes a query, which is basically the current input to the network, and matches it to a set of keys through a set of linear operations, or well, not necessarily linear, but a set of transformations. And the output will then be a weighted sum of values depending on how well the keys and queries match. So it's a lot like looking in a database. And here you see an example of how it works. So here we have two different sentences, one in English and one in French. And what you can see is that when you translate the sentence, the attention or the relation between the words is essentially along the diagonal, which means that the words can be translated almost one by one, except in this region, where you see that the attention or the relation between the words are reversed, right? Which you can also see from the English versus French translation, that in English you have the European Economic Area in that order, while in French the order is opposite. Zone economic area, European, right? So it's the complete opposite order in French, which is also reflected then in this attention map, or this correlation map that the attention mechanism generates. So let's see if this. So I think what I will do is that I will again assign you to a couple of breakout rooms, and you can discuss why this. I mean, this is a very brief introduction to the attention mechanism, but it's really not. It's really not that complicated when you understand how it works. So I will put you into breakout rooms again, and you can discuss why you think that the attention mechanism outperforms long short-term memory modules, and if this is kind of a general feature of attention mechanism, that it's always better, or if one sometimes actually wants to use some kind of recurrence in neural networks. So that will be the final discussion session, and then when we reconvene, I will just put you here in for a few minutes. When we reconvene, we can briefly discuss that, and that will be the end of this lecture, basically. I will open them now. Share my screen again. Let's see. So please share your thoughts, and we will just have a very brief discussion about this before closing this session. Yes, exactly. Better parallelization. That's a key point, because you can analyze in principle, you can analyze all data at once instead of feeding them in point by point. So that's an excellent point. So it's faster. So another point is that the network is not restricted to look only. Exactly. That was what I was going to say. There's no bias towards data close data. And this can be both good and bad, as you can imagine. I guess if you want to predict the weather based on previous data, you might not want the weather for, I don't know, January 1976 to be very important for predicting the weather tomorrow, right? So in some cases, you want to have data that is biased towards the nearest time points, and in the other cases, you don't want that. So that is both a drawback and a benefit of attention mechanisms. Yeah, but I mean, I think that is kind of the, I think any neural network is problematic for infinite time series. If you have infinite amount of data, at least.
Okay, I can maybe explain that a bit more. I see that I'm not muted here. So they mentioned it in one of the videos that was linked, I think, that you can't just have, like in a LSTM cell, you can just put data as you get it, like continuously.
Yes.
Which you cannot do with attention.
Yeah, exactly. Yes, that is a good point. Yeah, it analyzes everything at once in a sense, and it can be both good and bad also. Great. I think those are all excellent points. So I think with that, I will close this lecture, and I invite you to do this homework, where hopefully you will get a little bit more intuition also about how the attention mechanism works. Great. So thanks for today, and yeah, see you in the homework sessions, I guess. Great.